present a solution to Canada Math Olympiad 2022, problem 2. Firstly, we'll have a look at the statement. This problem is concerned with the function d that is defined to map any positive integer to the number of its positive divisors. We shall prove that the following identity is true for all positive integers n. d of 1 plus d of 3 plus ... plus d of 2n minus 1 is less than or equal to d of 2 plus d of 4 plus ... plus d of 2n. With this problem, it is really easy to get stuck for a long time. Personally, I tried comparing individual summons for a long time, because you immediately see that, well, d of 1 is exactly half of d of 2, and d of 3 is half of d of 6, and in general, for odd k, d of 2k is twice d of k. And you can apply this inequality many times right here, which seems very nice at first because, well, half of the summons on the left side are going to cancel out, but not all of them, because for large k right here we cannot apply that inequality because then 2k is not going to have a corresponding term right here. And yeah, you get some inequality after doing that, which turns out to be really difficult and weird to prove, and there's really no way to continue after that. So in this case, the way to go is really a much more global approach to look at what the left and right hand side tell us. To do that, we're going to take a more combinatorial approach. Instead of looking at the sizes of each of those summons, we want to look at how many times can one divisor contribute to different summons on both sides. For example, if we take a look at the number 3, then, well, 3 is a divisor of 3, therefore it contributes 1 right here. But it is also a divisor of 6, so we get a plus 1 right here, and this goes on left and right and so on. And this approach can be generalized, so instead of taking a look at how many divisors does a number have, we take a look at how many times does any integer divide numbers on the left side and the right side. Now we can look at a general odd integer k and to what summons it's going to contribute on the left and to the right side. For k odd, we know that, well, k is odd, 2k is even, 3k is odd, 4k is even, and so on. And therefore, if we color code both of these sums with, for example, green and blue, then, well, since k is odd, it's going to contribute to the sum on the left. If 2k does not exceed 2n, it is going to contribute to the right. Otherwise, all of those following terms are not going to contribute at all. Now 3k is going to be odd again, and we can continue this process up to the point where we hit some number that exceeds the maximum of 2n. In the end, we want to bound our green sum by the blue sum. Therefore, this case where k is odd, this alternating behavior works out really nice for us because we cannot really have much more green than blue right here. But since we are starting with a green term, if we are unlucky, then the last term is going to be green. And in that case, we're going to have one more green than blue terms, but never more. So we conclude that green is less than or equal to blue plus 1. We also should consider the case where k is even. But that case is way nicer because if it is even, then it is only going to divide even numbers and therefore not going to contribute to the green sum. So in that case, the green contribution is equal to 0. At this point, we see that we should be done, because for k odd, we see that it contributes about as much for the green as it contributes to the blue sum. On the other hand, every single even k only contributes to the blue sum. So this inequality should definitely hold. And we see that the best k to take a look at is k equal to 2, because, well, 2 divides 2, 4, and any other number on that side. So in that case, the blue contribution equals n. Since there are only n odd numbers k less than or equal to 2n minus 1, we are already done at this point, because any such number can only increase the left sum by 1 with respect to the right sum. So wrapping up all that we have, we get that the right hand side minus left hand side is nothing but the sum going from k is equal to 1 up to 2n of the blue contribution of k minus its green contribution. We already noted that for even k, this inner sum is always going to be non-negative. Therefore, all of this is greater than or equal to the sum of odd k between 1 and 2n of the blue minus the green contribution. And since we don't want to ignore all of the even k, we want to take into account that for k is equal to 2, blue minus green is equal to n. And this is now greater than or equal to the sum of negative 1 from k is equal to 1 up to 2n and k odd plus n, but this is equal to 0, and therefore we are done. In this video, we presented a much more visual but less formal proof than usual. Please tell us in the comments if you like that, and if you are interested in a more formal solution, then you can visit our website where we uploaded a formal proof as always.